Hi, how are you? I hope you're well. I mean, unfortunately, I've been still sick until for a week or so, but I hope still doesn't affect my teaching that much. Just to remind you that tomorrow at night there will be an optional tutorial where you can attend, and there will be a Zoom and also as well as a live section, and there will be record as well. So either it's optional. So you'll be reviewing the chapter 1 to 3. And also, if you have any question about the quiz and also the assignment, it'll be all there. So you can send him an email or just assume you just type the question and then probably you can answer it. So use the information there will be LSBC2, 6:30 to 9:30. I guess many of you are celebrating the holiday, but do log in the Zoom and see if you have anything to ask. There will be another additional second tutorial before the exam we have. But there will be, but in most of the time, you can always ask the other TA for Q&A. But this is a special arranged for you. It's provided by the TA, so which I do recommend you to attend if you have anything to clear up, because I do see that we are getting increasingly more difficult as the semester goes, pass through the descriptive statistics. And now we have more difficult stuff. So as usual, then we do notice things getting more difficult. And if you don't spend a little bit more time on it, then you would be a little bit behind. So let me very, very quickly review, because on the estimation, because hypothesis testing we have started already. So let's very quickly review estimation, because that the two chapters are closely related. So that we call what's the estimation? Estimation is the idea that you get information from the data, which is sample, and you want to extend the knowledge to the population, right? So it's just information from sample and to the population. And we do many ways to do it. We do point estimator and interval estimator. And particular, I hope you still remember the our main formula that would be very useful, right? This is the main formula. This is the interval estimator. When you have the sigma square, you know the population variance, which sometimes is good, but in most of the time it's not very practical. And the more practical one is this guy, but of course this guy have some limitation, because you have to assume the underlying population follow normal, right? So that is important restriction. And I have mentioned that if you don't want to assume normality, you have to use other more high-tech method, like numerical method, like bootstrapping or multicolor simulation, this kind of stuff. But it's beyond the scope of a class, so that's we start with this one. But this one is we use all the time, so we don't have to worry too much about that. In the last class, we also mentioned about a more fundamental question is how many samples we should get before we start, right? Because we are going to conduct a survey by ourselves, right? If we rely on other people's data, we don't have this problem. But if we want to get primary data, right? We get the data by ourselves, then this is a question to ask ourselves, right? How many observations we should get, right? And that depends on the precision you want to get at the end, right? So if you tell me what is the margin error, and this is the formula, right? So we have gone through this in detail through the examples, and I hope shouldn't be an issue, right? In one particular that is also interesting, if you still recall, is the proportion data, right? Binary data. And when a binary data, then turn out that you would use this formula, which is not something very surprising to you. We derived it. But in particular, if you don't know the pi, the population proportion, then we use the 1/2, right? That will give us because it's the most conservative one. That's give us this formula. And we, from this, understand why in many political polls in the US or other places in the world, 1,000 is enough, right? because that would correspond to roughly a margin error of 0.033, right? It's 1/30th. And that is the reason that why even in the US, in a very large population, then you only need 1,000, right? And also, and that's why in small, as in Hong Kong, right, we often do the survey. On yes, no question, we still need around 600, 700 to 1,000. It's not about the total population size, but rather the precision we want. Okay, so this is something that you do notice is uncorrelated with the population number you have, right? So that is something that is somewhat counterintuitive, I would say. And you do notice assignment has been released, so you can check out, work out the assignment and see if you have any question while you're doing it. Now, since we have a long chapter on hypothesis testing, so let's quickly go back to this one. Okay, so we'll do one sample and then we'll do two sample in the thank you. So that will be next week. We'll do two sample will be closely with the A/B testing, and that is an application of that. And one sample is closely related to the mention about the we are doing auditing application, and also we want to do a quality control. We want to see if things are equal to that or not, right? So just to remind you that what is hypothesis testing? Hypothesis testing is almost opposite estimation. Estimation is use the information of the sample to guess what is the population, right? Just to remind you, hypothesis testing will work. We have some information or some idea about the population, but we want this data to validate or to support whether our idea on the population is right or wrong. Okay, I hope I can, since we have time, I think we can draw the picture again. Probably you will remember our diagram, right? So we have a population here, right? And we have Mr. 1, right? Mr. 1, and we have Miss 2, right? We have an elderly 3, right? And we have baby number 4 here, right? And we know that this whole population, we have the mean of 2.5, right? That will be a population mean, right? In this particular example here, we have the population mean is 5, right? The question in estimation is you grab some people here and try to look at the sample mean and look at the sample variance, and we extend our knowledge from that, right? But now it's the reverse, right? Just to recall what is the estimation. Estimation is just you pick up these two person, right? It can be random, but in the case you pick up these two, right? You got sampling, right? It's sample, right? And then we have a sample mean of 1.5, right? And we use this X bar to estimate the mean, right? But to remind yourself, X bar is a random variable, right? It depends on sample you got, right? You got Mr. 1 and Mr. 2, 1.5. But if you got Mr. 1 and you got a baby 4, then you get the right number, right? You get 2.5. You got Mr. 1 and baby 4, right? But if you get also Miss 2 and elderly 3, you also got the right number. But if you get the Mr. 1 and elderly 3, you get the wrong number, right, too. So it really depends, but on average, it's right, because it's unbiased, right? And we know consistent and also efficient. There are many nice property there, right? Estimation, remember, is to the sample information to population, right? This is called estimation. And the idea, we go back from here, if we want to check if it's true or not, right? Of course, we don't know this number, is to go back to here. We pick up some data to check if this is true or not, right? That's called a hypothesis testing. So that is the, you go the other way, right? You have some idea of the mu. Of course, it can't be 2.5. You have no 2.5 done, right? But maybe some number, I think mu is like 2, or I mean mu is 3, so on and so forth, right? I don't exactly know who is inside there, but you try to look at data and see whether this is support or not, right? This is something we mentioned last Thursday. And I hope you understand what I'm doing, because that's very important, right? I mean, I just remind you that, right? Almost every statistics, right? You involve an estimation of a model and then you test it before you actually put it into use, right? Of course, if you are doing a very large data, your big data, then you probably can skip some of those steps. But that is a very classical way to do statistical analysis. Sorry. The idea of hypothesis testing is similar to the CORD, as we mentioned last time. That is, we start with a null hypothesis. You have a start with something, you want to see if data support or not, right? Same in the courtroom, you would just start with the assumption that the defendant is not guilty until evidence show the other way around, right? So that is a very classical do it. Okay? You have a two hypotheses. And we said the null or H1, so X0 is the one we start with, and then you see the data support the other way around, it's X1 or X8. And probably you ask, how do we have X null or HA? And then X null come with the idea that your boss may tell you or your client told you, right? As audit case, or in the quality control, right? It depends on what the government you test the law, right? So that is something that you would know. And as you remember, that is hypothesis testing, right? It's like whether the data is sufficient to reject or not, right? So basically, hypothesis testing would decide what is the thing that you would judge that is acceptable. You support the null, right? You support that is innocent, and when you support it's guilty, right? That is the idea behind, right? So that is important. And we also distinguish what is simple, what is null, right? Simple and composite. Simple is the one that you say only one value. Composite is more than one. And in your class, I mentioned that we will focus on the case where the null is always simple. The alternative is always composite. Okay. Of course, you can always relax this, but it's way beyond the scope of class. And I think for undergrad, that is something you would be facing. Okay. If you want to do further, have to go beyond B school. So I think that is something that we're happy with at the moment. And although there's only simple in the null, but the alternative has composite, but there are usually general 3 ways to be composite. So the most default one will be the not equal to. So just remember last time I mentioned what not equal to means something that you have no idea, then this is the best default one. Okay? But there are many cases you would want to focus on one or the other, right? So that would be the ideal. I mean, I mentioned the example. Last time would be, say this example, right? With a local club, then you want to take action only if this customer became older than you think, right? Then the H1, right? The alternative is more than, right? Because when it's less than 45, you don't really take any action, right? The same as you can imagine you are the government, you want to check whether the harmful substance is above some legal limit, right? If below, we don't take any action. If above, take action, so the same idea. And in the case of auditing, right, you would have a claim which given by your client, and the claim, the reference is like this, right? Of course, you can actually go to the system and check every single entry, but it's not possible to do it, right? In that case, you only say randomly check out maybe some branches with some year, and then check out the number, and then that is some evidence you're going to collect. And the thing is, as an auditor, you don't want the revenue you're going to attest is below or above, right? If below, then maybe the fabricating the profit, you're in trouble. If it's above, then also there's sorry, when it's below, it may be okay, wait this way. If what it is claimed to below what they claim, then they're fabricating profit, then you have trouble, right? If you go to the bank and borrow loan. If it is above what they claim, then it's basically tax evasion. So either way, you don't want to be different from that, right? You have trouble. And also, that's what auditor said, right? You have to say it's a unbiased estimate kind of idea, right? In the auditing principle. So so in a hypothetic, basically you would calculate a test you would calculate test statistics, and you would design at what value you would reject and what value you would not. Okay, give an example would be like the following, right? If you have a rejection, like you want to say the mu is more than as alternative, right? That means that the rejection region will be very large. When very large, they will be favor this alternative, right? When it is small, when it is the sample mean is very small, then the population mean is small enough, right? You ask the population mean is equal to that value. If your sample mean is like too big or too small, then you reject. So that is the idea. But don't worry, we'll maybe a little bit abstract. We'll give you the example directly. Okay. After we describe this type 1 error and type 2 error. So every statistics decision will involve two types of error. That would be something a little bit more complicated. Sorry, a lot of terminology because this topic has a huge amount of terminology. I already kept it the minimum. So I guess it's the last 3 to 4 concept. We actually go to something that we can operate. So the first is type 1 error. Type 1 error is because by probability, right? Even though the null is true, we can still reject it, right? Because remember the concept sample mean. Sample mean is normal distribution, right? Can be anything from negative infinity to positive infinity, right? Even though its true mean is actually some number, you can end up in any wrong hand, right? So in that case, you can make mistake, and that is called type 1 error. It's true, but you reject it. Okay, you reject the true null. That is type 1 error. Okay, and the probability of committing such error is called type 1 error. And and sometimes it's referred to significance level, and it's denoted alpha, and that is closer to the alpha that we use in confidence interval. Later you will see that it's very similar. And the rule of thumb is also 1%, 5%, 10%. We know it already. That is the standard rule of thumb. Okay. And this is a slightly little bit trickier question, but I have to slowly explain because this is a technique that we use all the time. It was not often before the day we have computer that easily, but now computer is so convenient that we will keep calculating this, what we call p-value. And p-value by construction is very difficult to understand. It's the smallest significant level that reject the x0. Okay, so this definition looks a little bit crazy at the moment. But later you will see is often the rule that we use to do the calculation. So what does this exactly mean here? Okay, let me draw a picture to help you to visualize what we are doing. Okay, and remember by central limit theorem or by normality. Okay, so suppose the x bar right? If a normal will be normally distributed, right? With the mean mu and variance with sigma square over n, right? So that will be something we learn from central near field, right? And we will have to decide, right, when we will reject or not reject, right? Suppose this is the case. So we'll say maybe this is A, right? Some number, mu is equal to A. Okay? And where alternative is mu bigger than A. Okay? So there's something we want to see with the data supporting this or this. Okay. And what it's going to do later we'll see, we will have a critical value with a number, which will say if more than that, we reject. Less than that, we're not, right? Because for the data to support this, it must be super large, right? If your data is like below A, then probably you would not say this, right? So it's exactly A, even you would not, right? So basically, if the data is in this region, you will not say anything, right? You will say, okay, it's not going to help you for X1, but it's X0, right? And the question is how far we go beyond A, right? Is it how much is enough? Okay. You will have a what we call the critical value, some value here. And we will say this is safe. I mean, this is going to support this guy. And this is going to support this one, right? And this line is called critical value. And how do we decide this critical value? It's close to that we said is the alpha. What is the significance level? The probability that we commit type 1 error, right? Because if this is true, okay, we can end up in the blue region, right? With some low probability, right? And how low is low is we decide. That's the alpha. Okay. So we make when we decide alpha, we decide this value, right? So how far above A is large enough to support X1 is the alpha we decide. You decide how much type 1 error you want to commit, right? Because even if this is true, it can be far away, right? It can still be there. So once you fix your type 1 error, you know how far is far away from A. Okay, let me repeat the statement here. Our hypothesis is saying that X now is equal to A, X1 is more than A, right? So you expect the data from the sample mean, if this is above A, big enough, then you would say favor X1 rather than favor X0, right? Fair enough. But how far is far enough? And because remember, we have a bias saying that we will support the innocent assumption, right? Presumption. We assume the X now is right. So every decision is based on X now, right? Just like same as innocent assumption, right? So we assume this is right. And how likely we make a mistake is alpha, right? Once we fix the alpha, we know how far we'd go there, right? Once we fix the alpha, because it's normal, once we fix the alpha, right? And if alpha is like, later you see, right? Depend on, I think it's 2.5%, right? Then this is 2 standard D, 2 SD rule. Okay. So once I fix the alpha, then I know my critical value and know when to reject, when to accept, right? So that means that once I fix the alpha, if my data is here, then I would say this data support X now. If my data is actually here, then we'll say my data support X1. Okay. And remember, this is how we get this number. This number will be just norm as inverse 1 minus alpha, right? Because alpha is the right-hand side, the left-hand side is 1 minus alpha, right? So that would be the number that, of course, this is only the z value, right? So this is number you have to be multiplied by sigma over root n, right? Times mu, right? So this will be the number, right? So this will be the number that when you get x bar, if above this number, this is a critical value, right? Then this will give us the result. Okay. Is that okay? But now once you know that, then I can define p-value. Okay. P-value is such that instead of fixed a alpha, okay, you calculate at what alpha you just got rejected. So if your data is red here, the p-value will be just this area. This is a p-value. Is the significance level such that you just reject it. Okay? And you can imagine why in the old days it's not doable, because you need a lot of computing power. Before you just compare standard thing, but that is p-value. And of course, you compare p-value to your rule of thumb, 5%, 10%, 1%. Okay? If this p-value is small enough, then you would reject x1, right? So that is the idea of the p-value. Okay. Either you compare, so that's why there's always two ways. One is called critical value method. That's compare your sample mean to this value. The second method is the p-value method, is what I said. You calculate area. If area of this is less than what you want, type 1 error, 10%, 5%, 1%, then you reject. Okay. So don't worry, we will be, this is a little bit very abstract. We'll get into exactly the example there so that you will know how do we do the calculation. So let's do the calculation. So as we said, this is photonormal. And if you know the sigma square, do the z. If you don't know, use t, right? This is something we learned from the estimation. So that's exactly the same. So that's why we teach that, and then you will see this is very closely followed. So let's just do the example. So this is with the bell curve on the sample mean. And this is what we call the test statistics. Okay. You will do is, because under the null, your claim is A. So I take your claim, and this one should follow standard normal. Okay. Once with that, the right tail test will be just as we have seen. We will have mu equal to 0, mu bigger than A. Okay, mu equal to A, and then we need to check these test statistics. And either we've used two methods. Either you look at the critical value, or you would do the p-value. Okay? So let's look at the example, because I guess this is not understandable at the moment until you will see the example. Okay, let's see the example. So let's closing out the example. So the example is following. So consider we have a normal distribution for the sample with SD is 4. Okay. So with X here, we have a bell curve, and mu is unknown. Okay, but we know this sigma square, or sigma is 4, okay? Not sigma square. Okay, this is what we know about population. We don't know the mean. We want to check it. And what we do is we have a sample n equals 64. Okay, and sample mean is 7. And I want to check the hypothesis mu equal to 6. Okay, so we claim this is 6. Okay, what does that mean? It means that the sample mean will also be 6 here under the norm. But of course, this will be much narrow, right? Because this will be sigma square over n, right? As the variance, right? So that's the case. Okay. Under now this would happen. Okay. This will happen. So the question would be the following. The data tell us it's 7. So we're here. Okay. And our H1 is more than 6, right? The question is 7, is this sufficient evidence to say we support H0 or H1? In the other words, is the distance between what we claim and what the data is 1, right? Is this 1 big enough or small enough? Okay. It's hard to say, right? But we study the statistics, right? The distance will be measured by this area, right? We are asking ourselves, is this area big or small? If this area is small enough, then we say far away. Right? Is that clear? So is it 6 and 7 is big enough? We'll use the idea this area, the tail, beyond 7, is it big or small? If beyond 7 is very small, that is so impossible, right? So it's beyond reasonable doubt that we will in favor of H1, right? So how can we calculate this? Because we know it's normal, then what we're going to do is convert this to Z, right? This is 0. And what is 7 down there? Okay. 7, how do you convert this, right? Is this the distance, right? 7 minus 6, right? And divided by how many SD there? SD there will be 4 over root 64, right? So it will be 4 over root 64, right? Because SD is sigma over root n, right? This is SD, right? Over that. So it's 1 over 4 over A, which is 2. Okay. And the question would be 2, what is the area beyond 2 here? Right? So if we notice, this is 1 minus norm S inverse 2, right? Because 2, we calculate the left-hand side. Left-hand side is norm dot S dot inverse 2, right? 1 minus. And the answer is 2%, right? Calculate that. So this p-value method tells you it's 2%. So as long as you use the alpha, you decide what it is, but usually 5%, which is larger than your 2%. Then you say this is small enough, the area is so small, 7 is far away enough from 6. Then you would say, I would support H1 rather than H0. Okay, of course, if you say, I don't use 5%, I use 1%, then you say it's not enough. Okay, it's your decision. What is alpha? Of course, in the exam, I give you the alpha. And but of course, in the real world, you decide what is sufficient or not. But in standard practice, it's probably 5%. But of course, there are other scenarios, right? Because suppose later you see if I have a big data, then probably I will have a very small alpha. But in the classical case, you're learning 5% is the fixed sufficient. So compare the 5%. So in this case, 6 and 7 is large enough distance because area is so small, I will claim I support H1. Okay? So as the this is method 1, the p-value method. Okay? Another method is what we call the critical value method. Okay? Critical value method is not to calculate the 2, but we calculate what is 5% there. Is it beyond the point of no return or not? Right? It's a critical value. The question is asking us to calculate this. Z 0. I want this 5%. Okay. And how to calculate this? It's just norm S dot inverse, right? Or no, 95. Why? 0.5 on the right hand side, left hand side is 0.95. Then this would give you, we know this very well. It's 1.96, sorry, 1.64. Right? And remember, our 2 is here, right? Because it's 1.64. 2 is deep inside the region of rejection. So you also reject. Okay? So you can use this method or this method. Okay? And as I told you, why we have 2 methods in the old days, because computer reason, you only want to check tables. This is more common. But now, with computer, this is more common. And doesn't really matter which one you use. But I think people now recommend p-value because you know the exact number is getting more precise rather than the critical value. But I left you to decide which one to use. In the assignment, probably I asked you to do both. But in the exam, you can, I think, unless I specify which way, you can do whatever you like. Okay? Is that clear? So the p-value is our critical value method, right? Just like we just ask ourselves how far is far enough by deciding what alpha you want. Okay? You decide what is the type of error you want to come in, right? You have to make your judgment. What is? But do remember that there's no free lunch. Okay? And by making the type 1 error lower, you are leveling up the type 2 error. Right? Type 2 error is the if type 1 if the null is false but you fail to reject it. Right? But there is something that maybe a little bit too difficult for you at this moment. Is that okay? Maybe it's good to do another exercise and then before we go to break. Okay, that will be similar, but now we're left hand side. Okay, same idea here, but we're going to see the left hand side. And of course, if the data, the sample mean is very small, then we reject. The question is how small it is. Okay, is it sufficient small enough? Again, the idea is the area. Okay, but let's go to the example, then you will see, because I guess this type of test is contain a lot of detail, which will not make sense until you know how to operate them. And when you read them back, you understand what's going on. So again, the same question here. I have a population with normal bell. I don't know the mu, no idea. I know the sigma is 4. Okay, this is X, right? And I want to test hypothesis is 6. Okay, so once it's 6, so I know this is 6. This is by the H now. And the question would be, I want to see this is true or not, right? How can we do that? Is to look at the data, X bar, right? Is it sufficiently below 6, right? So it is X bar so 6 here. right? This will be sigma square over n, right, with the variance. And the question would be now, the data so as is 5. The question is it 5 low enough from 6, right? Because the actual one is below 6, right? If less than 5, sufficient enough, then it's yes, right? So the criteria is checking if this area is small enough, right? If this area is small enough, then 5 and 6 is far away enough, right? And how small it is our alpha. We have to decide what is our time error, right? We decided what is the time error, that we decide our point that is small enough, right? Because time error is how much error I'm going to admit, right? Because even if it's true, we can have this small value, right? So once we decide our time error, we know what is so small to get rejected. Okay. Now we know this is calculate this sigma over root n, right? Will be 4 over root 64, right? So it's again 1/2. Okay. And we know the SD of fixed bar is 1/2, so this is basically 2 SD from the mean, right? And 2 SD from mean, you know, normal 2 SD is enough to say far away enough, right? But we actually try to do that, right? So this is Z, okay? 6 become 0, and 5 become how much? -2, right? Because it's 2, right? Because the SD is like 1/2, right? Distance of 1 means 2. So that is like this. And we calculate this area. We ask, is this area small enough, right? This area given by norm as inverse -2, which give you this number 2%. So this is smaller than 5% if you do 5%. But if you 1% is not small enough, use 10% is also small enough. So you decide alpha, and this gives you the answer. And again, if you fix 5% here, then you can also calculate critical value, which is -Z alpha, right? Because this is Z alpha, right? So this critical value is given by, this is like 5%. So it says norm as inverse 5% will give you -1.64. Okay. And since -2 is here, okay, so it is deep inside the rejection region, so you reject as well. So I hope this tells you how we do this hypothesis testing, right? If this is too small, too big, right? It's just supporting the alternative, right? And then how big or how small depends on area. Okay. And that would give you the idea. And then you can either do the p-value or the significance level. Either of them would work pretty well. Okay. And I guess I overrun by 4 minutes, so let's have a 15 minutes break. As usual, then I would do the U-reply. Let me clean up the screen. Okay. At a break of 15 minutes, we'll resume at 3:45. Hi, welcome back. I hope you have a good break and then notice that it was very tiring. I hope the Wednesday holiday will make you take some rest. As you're aware, I've been sick, so that's why I've been taking rest, not doing too much stuff. So that's why I become much better than I used to be. But oh, I should show the answer. What's life? Well, that's a deep question. The philosophical question is basically underlying all the philosopher. What's life? I really don't know. It's a kind of how you define it. It's your own definition. Of course, there's a life that economists they will say, okay, say pursue happiness, right? Maximize your happiness, maximize utility, right? I mean, you ask a business school student, maximize your income, maximize your money, maximize your fame, and that's life. And life is different when you are on your own, or once you met your significant others, you get a kid, and it's also different. Different stage of life would have different meaning. Of course, if you're religious, it also have religious meaning. But I don't know if you care about things at the end of the life, then you care about the limit, right? Or and when n go to infinity, right? Rather you get the consistent estimator at the end of the thing. So maybe that's a good answer to that. But I think it's just like I don't know, to be honest. I don't have a good answer to that. I think I'm searching meaning of life, but I think it's more important is how to live a life, right? How to survive first, right? I guess now you need to survive this class, to study. I think that is something I can answer. But to be honest, I really don't know a good answer to this question. Well, if I know, I will become philosophy professor, not an econ professor, right? So what I know is just how to maximize utility, right? How to maximize that, how to do a decision here, right? So, but there's a question. Well, it's a good question. So it's good. Everyone got it right. What's the weather? Is it cloudy? Let me see. Is it really cloudy? Oh, maybe you're right. A little bit cloudy. Not really too bright. You're right. It's not. Oh, yeah, actually more cloudy than sunny. Yeah, C test, this is something we talk about. And reject those outside the range. Yes, that is what we say, is try to reject when it's favoring our alternative. If the p-value, the c-test, the critical value, yeah, that is exactly true. So I'm glad that people here know what's going on. Okay, the speed is okay. I think most of you said it's okay. It's not too fast to snow. And one of you said it's not easy to follow. Because as I told you, we're getting more abstract. So you cannot be easily understandable by one grasp. You probably have to read the material again. Or you can watch the Zoom record lecture again. In case I told you you can't sleep very well because of you worry about the midterm or final, it's good to watch my video. It helps you sleep very quickly. I mean, that would be an advice for me. Boom. We're tired. So at least we have less than half is super tired, but it doesn't seem to be very promising because we have 30% of you are not quite tired. Hopefully on first day we met again, you will not so tired after you have a holiday. But and do remember Friday we have a big thing. Trick or treat, right? So get more candy. No, I am sleepy. Yeah, I've been sleepy because of throughout the weekend because I take drugs. I mean medicine, not the drugs, but so that's why I keep very sleepy. But I didn't have drug today, so that's why cough a little more, but still awake. So let's return to our C test, right? So that's we know how to test it, right? To see the data is supporting the one or not, right? So that's the idea. So now let's get to something I think is slightly tricky. It's what we call the two-sided test. We said mu to A is normal, but the alternative is mu not equal to A. So that is a little bit tricky. It's not about the method, but it's about some details about the p-value. And let me illustrate the operation, then you will see why it's a little bit tricky. Now, again, the question is the same in the sense that we have a standard deviation of 4, okay? And sample size n is 65. Again, a mu is 6, but the changes I text mu not equal to 6. Okay, so that's a little bit tricky part. So let's remind ourselves that because of this normal assumption, our x bar also follow normal. Okay, and the center of data will be according to x0 is 6, right? And this will have a sigma square over n as a variance. If you like, this will be the SD. So it's up to you which one you use. This is SD, right? So now the question is not the H1 is not equal to. It's a little bit tricky because in that case means that if it's too large from 6 and too small from 6, you reject, right? So how to decide our rejection region would be too small, too big, right? So you'll be too small, so too big, or too small. Okay. And this should add up to alpha, right? Because even it's true, you can add up in this area and will reject, right? So these two add up should be alpha. That means that if we don't bias over one or the other, it will be alpha over 2. It's alpha over 2. Okay. So that is something that is a little bit tricky here. Okay. This is alpha over 2 is assigned it on both sides because you don't know before we do the data where it is. Okay. So that is the only tricky part. Because it's one-sided, it's very obvious. And two-sided is slightly little bit tricky. And our question is is our 5 is here. Okay. I don't know 5 is here or 5 is here, right? Because if 5 is here, then you reject, right? If 5 is here, you don't. Right? So the question is whether 5 is in one case or the other, right? So either the distance, 5 is below 6, right? Is it small enough? Okay, so that's a question. So it's nothing complicated, right? Just now the alpha have two-sided. That is only difference. So what we're going to do, let's use the p-value method, right? And let's ask ourselves, right? Convert this to Z. This become 0. And what is 5 here? Okay. Remember, this is still 4 over square root 64 is still 1/2, right? So this guy is still -2, right? Because this is it's still 2 SD below the mean. So the question again is, what is this value, right? This value, again, come from the norm S, this, right, 2, true, right? So because from -2 you find the area, right? And this will give you this answer, right? Norm dot this dot true should be 0.4%, right? But sorry, not 4%, it's like 2%. Okay, that's 2%. Just show it Excel to make sure that you know the operation. So we have the norm this 2 true. Sorry, so -2. Right, it's -2. So -2 is 2%. So -2, sorry. So this is like 0.02%. So you will see at the end, the p-value I have multiplied by 2. Why is the case? Because remember definition. The definition is p-value is you adjust the significance level such that you just reject, right? But this area, you divide by 2, right? So that's why the p-value you have to multiply by 2. Okay. So let me repeat the statement. The p-value is just the alpha such that you reject. Okay. And the area you get on the other side is the alpha significance level over 2. Okay. So that's why when you calculate the area, it's just half of that. So you can multiply. So the p-value you have to multiply by 2 to get the answer. And this, of course, compared to 5% or not. So that's why you get this value. Okay. So that is very tricky because it's not easy to understand why the p-value you have to multiply by 2. Because you start from definition, what's the p-value? P-value just adjust alpha such that you got reject. But the alpha have to be divided into both sides because two-sided test. Because you don't know actually is before you do the sampling, it's actually go to 5 or go to 7, right? It can be either way around, can be more than 6 or less than 6. So you don't know before you get data. So that's why when you design it, once you calculate this, you have to multiply 2, right? So you get 4%. So if you don't want to make your mind difficult, then you could always just say when two-sided double the p-value. The p-value double the area. When one-sided, just the area. Okay? And that will be easiest for you to think. And again, you can calculate the critical value, right? But you know this 65, 95, 90, 99 rule. 95% is just 2 SD, right? or 1.96, right? So that means that if you want this area add up together is 0.025. This is negative 1.96. This is 1.96. Okay. And your 2 is exactly inside. Negative 2, right? So it's deep inside the region, just slightly above, slightly inside the Richardson region. So you reject. So this is known as a famous set test, right? So either use the p-value method or critical value method will deliver the idea. Is that okay? So if you don't get it, don't worry. We'll repeat this with the t-test, the same thing. The t-test is the same, but because we don't know the sigma, we use the S. And the t-table with the check is appropriate t-table. Okay. Let us go to the t-table. The t is the same, right? You just replace the sigma of S. Okay. Let us go to example without going too much into the details of the statement, because once you know the example have been doing, then you would not be too surprised how we do. Okay. We start population with normal. It's important because without normal, then we cannot use the t-test, right? Remember, that's something very important. So under this, if you get a sample, so under the null, and this, we know this will happen, right? X bar will mean 4. It's a bell curve. This is sigma square over root n, so over n, right? But we don't know this guy, right? So the bell curve is not really helpful, right? But at least what we want to check is this guy is X bar is 5 here, right? So we want to know the X1 is mu bigger than 4, right? So that's the question is this area big enough, right? Because 5 is more than 6, more than 4, right? So is it the distant one is sufficient, right? If we know sigma, then we can easily calculate, right? Because if no sigma, n is 16, right? We know the answer already, right? We know how to do this question very well. If we know sigma, because from the shape, we can see the area is big enough or small enough, right? The question is we cannot do z-test because we don't know sigma square, right? Without sigma square, we don't know this area, no idea. But the good point is, even we don't know, Mr. Student figure out that it's Tn minus 1. Right? This is T15 because n is 16. And this 4 becomes 0. And what's this number? Okay. What's the number here? What is 5? And because we don't know the sigma, we replace by S. Right? S is what? S is 2. So this is asking 1 over S over root 16, which is 1 over 1/2, which is 2. Okay. So if you don't know the sigma, you replace by S, right? And S over root n, right? S is 2, root n is 4, right? So the distance is also still 2, right? Because the estimated standard error is 1/2, right? Because S over root n is 1/2. So the question is just asking, what is this area? Right? 2 is Tn minus 1. So what are you going to do? This area? Because this T table, you know the area on the left-hand side. The right-hand side is 1 minus T dot this 2. Degree of freedom is 15. True. This will give you the p-value, which is 3%. Right? Because you look at number, look at area, you should T this. Right? In case you don't believe me, look at Excel. One minus T dot this 2, 15, true. Which is 3%, as we have shown you. Yeah. Do this 3% here. And alpha is 5%. So it's far away enough, then reject. So this is known as t-test. So you know, we have played this class after you know the t-test and the c-test. Then you can write in your CV, right? I think that is something not covered in the, at least t-test is not covered in the M1 or M2. So there's something now, we go beyond our high school curriculum, right? So far, you are not different from high school students, who those who take an M1, M2. But now, after this class, you know t-test, which is not covered in the high school curriculum. So t-test is new. Okay. So of course, the other question will be, can I do critical value method, right? Which is also question, which is asking you the following question, right? The same question, T15, 0. What is 5% here? Right? And this number, we simply just area to horizontal, it's just T inverse 0.95, 15. Because right hand side 5%, left hand side 95, and degree of freedom 15. This would give you 1.75. And our T is, so this is 1.75. And our data is 2, so it's deep inside the region. You're going to reject. Sorry. So you can see the t-test is there. So nothing very deep here, right? The c-test and t-test is the same thing, except you change the denominator to dy, right? Because look at this again. This only difference is this guy is S. Before it was sigma, right? When you don't know the sigma, you replace by S, you have to check the T table. Same as you do interval estimation, right? If you know sigma, you use the Z, right? If you don't know, you use the S, but you use the T instead. Is that clear? Okay. If you have no question, then we go to another example, because what we do in this class is just working out a lot of examples like this, make sure that you know the procedure, because this is the procedure that you understand. It's more the algorithm, just like this, You follow this and this and this and just done, right? Again, the question will follow. Assume the population of normal distribution. You want to test whether mu is 4, mu less than 4. And you collect the data with sample size 16. The sample mean is 3, and sample standard deviation is 2. You don't know sigma. Okay. And looking at this, sample mean is 3, mu is 4. So we need to do a careful check, right? Because if mu is like 6, then you can just go, X bar is 6, you can just go home, right? If only X bar is less than 4, you need to do anything to check. So very boringly, you just do it again. X bar is here. You know this is going to be the sample, the population mean is 4. So 4 is here. You know this is the bell curve, right? And this will follow the sample mean, like the variance is like this, right? So the real question is, now we have 3. So the question is, 3, is it far away from 4? Such that I would like to support X1 rather than X0, right? X1 is less than 4. The question is, this is so small enough. And again, the answer is this guy, right? In this area, small enough, smaller than alpha. The alpha is the tolerance rate. Whether we think alpha is, we're going to reject this one, right? The alpha is the thing. If this is true, we can still reject this, right? This alpha is a tolerance level. It's the type 1 error. And we set 5%. So ask ourselves if this area is less than 5% or not. And we know that we can't calculate this without knowing the sigma. Right? We can't do it. So how can we solve this problem? Is we know that we can look at the T 15, right? Because N is 16. In that case, 4 is 0. And 3 is what? 4 is 3 there. What we do is just like, how do we convert this? 3 minus 4 over S over root N. Right? So it's just -2. So the question boils down to, is this area small enough? Okay. And we know it's T15. So it's not hard to calculate that. Simply T, this, -2, 15, true. And this will give us 3%. And we say 3% is far away enough because it's smaller than 5%, right? So it's small enough. Then our threshold, which is type 1 error, right? Type 1 error is, if it's true, how small we say small enough to reject, right? Because right? And again, this is called p-value method, then we're done, right? So we'll reject X1, right? But if you don't want to do it, you can again do the critical value method, right? Which is asking ourselves T15, 0, because reject on the left-hand side. So we ask ourselves, what is 5% here? Right? And the answer would simply be just T inverse 105, 15. Right? And this gives you negative 1.753. And since your data is actually 2, negative 2 here, so it's inside the rejection region, you also reject. Okay. So that is either way will work. I slow down a little bit because I will do a both side t-test, then that will conclude our day. But I would like to see even a question, because you can see today we just do very mechanical thing, right? Z-test, left tail, right tail, both tail. T-test, left tail, right tail, both tail. Nothing very deep here, just law-like procedure. Because we don't derive any formula here, right? But the main thing is very simple, right? Because once decide our alpha, we can tell what's the line that you reject or accept. Right? It's far away, supporting H1 or not. That's it. Is that okay? I mean, if you never understand you ever study about testing, it must be new to you. But if you've done that, then it's something piece of cake. Okay. For the very last one, let me go very slowly again to make sure everyone got it. Because this is the one that summarizes what we're doing. Okay. So let me do it slowly. Okay. Again, we assume population is normal, a bell curve. And we want to see the population. Is it actually equal to 4 or not equal to 4? So that's a question. Okay. Then what we're going to do, look at data. Okay. Look at data with sample size 16. Turn out the sample mean is 3. Sample standard deviation is 2. Okay. And of course, 3 is not 4. So the question is 3 far away from 4, such that we can't take the H now? We will say H1 is the right thing. Okay. So remember, we have normal. That means that X bar, the sample mean, before we do the sample, is a normal distribution. Centered, if this is right, center at 4. With a bell curve. With some variance like this. But if this is the case, so we will mostly around 4, right? So if this is, the answer is like somewhere 3 here, that's what we found. The question is 3 far away from 4, right? And remember, we're doing a two-sided test, right? Because we're saying that not equal to 4. So that means that we will be not very happy if this is far away from 4 on the either side, right? We will have alpha over 2 here, alpha over 2. Remember, alpha is our significance value, significance level, which is the type 1 error we're going to accept, right? Which is, even if it's true, it can end up in these two areas, right? We have to decide what is the maximum type of error we're going to take, right? And we have to say this is area, and beyond that, we just let it go. right? Because even if it's true, it can end up in the green area. So we have to decide what is the type of error. Sorry. So the green area will be the thing we design. Okay. And unfortunately, we know n, but we don't know sigma square. So this is not directly computable, right? We can't really calculate it. So what we're going to do is to convert this to the t, which we can do computation, right? Because t15, 4 becomes 0. 3 become 1. How to calculate this number? Will be just 3 minus 4 over 2s over root n. N is 16. So it's -2. Okay. So that will give us the answer, right? So 2. So the question would be, what is this area? Remember, two-tailed test, two-sided test, the area is not the p-value. We have to multiply by 2. Because this is, remember, it's the smallest alpha that we got reject. Right? So because the area is over 2, so you calculate area that multiply by 2. So what's this area? This area is simply t, this -2, 15, true. And the p-value will be 2 times. Of course, because the p-value will be 2 here. Right. This will be, add together will be the p-value. So that's why I multiply by 2. And turn out this is 6%. You can easily check the Excel. That means that if you use 5%, you can't reject it. So you use 5%, then you will say, okay, this is not far away enough. So you will say, okay, I will stand with X0. If you want me to reject X1, come back with more data. Okay? This data you give me is not sufficient. If you really want to do it, go to the data again, check, get more data for me, and I can see. At the moment, I can't reject. I would take X0. The defendant is innocent, is not guilty yet. Collect more data for me. If you really want to reject, maybe collect one small data, get a larger sample size, you may be able to reject. But at the moment, it's not. Okay? So that would be the answer. So you can't reject at 5%. Of course, if you use 10%, you can still reject. But 5% is not. Now the last part is talking about the significance level. Sorry, a critical value method. 0, T15, right? The question is asking this area, add together is 5%, so it's 0.025. This is 0.025. So how to calculate this number? With T dot inverse 0.025, 15. Okay, this will give you -2.1314. Okay, and you will notice 2 is here, -2 is here. Okay, so it's not in the region. So you do not reject X0, or that would be the conclusion we get. As I said, you can use p-value or critical value method. You don't have to use both. If assignment not asking you to use any particular method, you can just pick up one of them, unless I tell you one of them to allow. So I guess now you should be happy because you know the t-test, you know the z-test. You know one-sided, left tail, right tail, both tail. Okay. So that is very important. Okay. To conclude, I'll just write down what we covered today, which is something quickly in 1 minute. You learn two things, C test and T test. Okay. If sigma square, if yes, you know, you go to this. You don't know, we don't know. Okay. It depends on mu to A, and if H1 is mu less than A, there will be H1 mu bigger than A, and H1 is mu to A. Okay. This is left tail test. Left tail. This is called the right tail test. Right tail. This is both tail. Or one-sided or two-sided test. Okay. So same for the T test. Okay, the same thing. So I'll see you on Thursday. Enjoy the festival, climb the mountain. Since you're in CHK, you climb every day, right? So don't have to celebrate specially, but you can walk more over the campus, have fun with your friend and family. Bye-bye. Enjoy the holiday.